and welcome to your lesson on the Millikan oil drop experiment. Our hero for the day is Robert Millikan, and he performed at the beginning of the 1900s a pretty ingenious experiment to try to discover if there was some fundamental smallest quantity of charge that existed in the universe. That is, does charge actually exist as whole number multiples of some smallest charge? Or does charge grade into zero into any other number? Now this experiment was situated just when quantum theory was being born, and a lot of theoretical physics and experiments were being done to try to determine, was energy quantized? That is, does energy itself come in smallest number of or smallest packet of information, and only then released in equal packets of that value? And so, situated, this experiment was really important. Robert Millikan set out to find one of the fundamental physical constants in the universe. And there are a few of these, and we'll get to know a few of them as we progress near the end of the unit. And this fundamental physical constant that he tried to find was what we call the elementary charge. The elementary charge. That is the smallest notation of charge that exists in the universe. And so he came up with this pretty cool experiment that we can see here. It kind of looks like a distillery of some kind, but you can see that there is a microscope, and this guy right here is like an atomizer. So you squeeze it and it sprays out whatever fluid or solid seems to be in there, like a powder, and so it makes it into a mist. And then we have this big tube, and this big tube you can see is connected to some kind of voltage. And at the top we have a plate, at the bottom we have another plate, and this microscope looks in to see what's going on. Now we also had a light source that's set up. That's what these tubes here are for. These are light sources, allowing a small beam of light to enter into the chamber. Now this is pretty cool experiment, and we're going to today walk through exactly what the experiment was, what he found, and the math that he used to discover this elementary charge, the smallest possible charge in the universe. Now the essence of Millikan's experiment is to create a microbalance, that is a hollow cylinder where multiple forces are balanced. And if we can balance those forces, we can then do some math to figure out the different characteristics of the system that is in balance. Let's take a look at the insides of this microbalance. And the microbalance, this is the first one. And they are used even today. In fact, one was used, a pretty massive, technologically advanced one was used recently to redefine the kilogram in terms of Planck's constant, which is another fundamental quantity in the universe that's related to an object's energy. And you can look that up on YouTube. I know there's some, Veritasium has a great video explaining how the kilogram has been redefined using this microbalance. So let's take a look at what exactly it is. Let's zoom in here. Okay, so I've introduced to you kind of the macro components of this microbalance. We've got a DC supply, and you can see that some charge is going to the top plate, and some charge is going to the bottom plate, just like we saw in the capacitor setup. So this top plate is going to achieve a positive charge, and the negative plate will achieve a negative charge. So we can create a potential difference across the plate. Now if we were to draw in the field lines, the lines of force for a positive test charge, these guys are going to come down like this, these lines. And what that means is any positive charge that enters into this chamber is going to be attracted to that negative plate and repulsed by the positive plate. And that really is the secret of how it all works. You can see the light source. And the light source's only objective is to allow the microscope here to zoom in on these little oil drop particles as they're in the chamber between the charged plates. The atomizer, right here, guess we should use a color. The atomizer, its job is to take oil from this little red reservoir and atomize it. That means not create them into atoms, but to separate the fluid into microscopic particles of different size. And as these particles are atomized, they rush through the system, and as they rush past other droplets, they rub up against them, and some droplets will achieve an electron, more electrons than a neutral state would have, and some would have less electrons. So we have some positive charges resulting and some negative charges on these oil drops. You can probably see where we're headed now. As these oil drops fall into the chamber, any charge that is positive, any oil drop that has a positive charge is going to rush to the bottom plate. However, any charge that is negative is going to be attracted to the top plate and repulsed from the bottom plate. And if we can get the voltage just right, so the potential difference just balances the force due to gravity pulling down, then we can levitate that oil drop. Now, in order to make that potential difference exactly what it needs to be, we adjust the DC power supply. We adjust the potential difference to make an oil drop hover. Let's take a look at the math to see how that all fits together. So we're going to simplify even more Millikan system here and develop some math. So we have a top plate and a bottom plate. Now this diagram here, we're actually going to make the top plate negative, so let's make that negative, and this positive. That way we're really interested in a positive charge, getting a positive charge to levitate. And the electric field lines in this guy are going to be pointed up. The electric field lines are going to be pointed up. And we're going to have a positive plate at the bottom and a negative plate at the top. And we can control that potential difference by adjusting the DC power supply. And that's going to have some voltage V. Now we know the separation of the plates R, and we know how important that is. So if we have a positive charge, that positive charge is going to experience two forces. One force down, which is due to Fg, and another force up, which is Fe. Let's take a look at how we use this pretty simple but ingenious setup to come up with that fundamental charge. Alright, here we go. And we can understand how Millikan used this microbalance, this electrical microbalance, to determine the charge by comparing these two forces that are acting on us. So let's try to describe these two forces. We know that the electric force is equal to Q times the electric field strength. And we're going to assume that the charge is positive here for this model. And the electric field lines point up. we can carefully adjust the potential difference so the falling drop comes to rest between the plates. It levitates, it's hovering. That means when that is happening, that the electric force experienced by that charge is equal to Fg. Now, we previously discussed that the electric field between two charged plates depends on the potential difference, delta V. So we can also say that the electric field strength depends on that potential difference, delta V, and the distance between those two. And the distance here, of course, is the R. Now, delta D is that plate separation, and you explored how important that is when you played around with capacitors. So knowing this, we have an expression for Fe being Q times the electric field strength, and that's going to be equal to mg of the oil drop. Let's try to isolate for Q. Let's try to find that charge. So Q is going to be equal to mg divided by the electric field strength, and that's just a rearrangement of this guy right here. So you may be able to see where we're going. If we can express the electric field strength in terms of the voltage and the separation of the plates, we can come up with the charge of that oil drop. So let's make that substitution and see what this looks like. We now have the Q of that oil drop is equal to the mass of the oil drop times the gravitational field strength near the surface of the Earth multiplied by the displacement of the two plates divided by the potential difference. Now, here's an assumption that happens to be true, that if we can measure the potential difference of our batteries and the plate separation, then we can know the charge of the oil drop. If we can measure the drop's mass, this is the kicker right here. How do you measure the drop of that mass? Well, what Millikan did, and I think he probably ruined his eyesight doing it, this is where the microscope comes in. So once he had an oil drop that was positively charged levitating, he took a measurement of that potential difference, and then he turned the voltage off and let that particle drop. And this is why it's called the oil drop experiment. And he could time how long it took that oil drop to travel a certain distance, and from that he could measure the mass using our understanding of Newtonian kinematics and dynamics. And we won't discuss that here, just for ease of simplification. He did this many times in a dark field, probably ruined his eyesight, thousands of measurements, and he came up with a table of charges. Now, the amount of charge in each drop, of course, is going to be different from each other, depending on the mass, the size, the actual charge of it. But he wanted to ask himself, all the charges that he recorded, was there something in common? That is, were they whole number multiples of each other, where Q is equal to some multiplier, whole number multiplier, times that fundamental constant E. And indeed he found, with very minimal wobble due to his experimental, that the E, that fundamental charge, was equal to what we now accept to be the charge on an electron and the charge on a proton. These two charges are equal. And this was pretty astounding, because here's another example of subatomic particles adhering to some quantized story. That is, that there are packets of defined numeration. It's like going to a grocery store. You can only buy things in cents. You can't buy things in half a cent. You can only pay with a minimum amount of cent. And so the cent, the value of the electrical cent in the universe, happens to be this. And Millikan's oil drop experiment was repeatedly done and still is in some universities as an educational tool, and it always kind of comes out and to be true. And not only that, but it is just incredible that such a simple experiment can uncover one of the fundamental truths that exists in the universe. In the interest in kind of understanding, because this oil drop experiment pulls together everything we've talked about so far in the course. You kind of need the course in order to understand this experiment, but it's not insanely complicated. That's what's so beautiful about this, is it takes the simple Newtonian physics that we've been exploring, puts it together with the emergence of our theory and understanding of the electric nature of matter, and puts it all together. And what I'm going to ask you to do is to be able to solve problems in a Millikan type experiment. That is, if I give you two horizontal plates and there's a potential difference of this across them, and they're separated by a certain distance, and you should be able to map out the electric field lines, and you should be able to do the math. I may ask you to find the mass of the charged object. You could possibly find Q as well. So we'll take a look in your textbook, play around with some of this information. These formulas should be on your formula sheet, and you should be able to walk through this logical progression, that is understanding how we can apply balancing forces with an electric system. All right. Hope that helps. We'll talk to you later.